Hello, this will be a demonstration of proposition 7 from book 6 of Euclid's Elements, which says that if two triangles have one angle equal to one angle, and the sides about other angles proportional, then the triangles will be equiangular and have the sides about equal angles proportional. We're then given the triangles A, B, C, and the triangle D, E, F, A, B, C, D, E, F, such that the angle ABC is equal to the angle EDF, and AB is to BC just as DE is to EF. So instead of the sides about the equal angles being proportional, we have the sides about some other angle, or about two of the other angles being proportional. In this case, the sides about the angles B and E. Okay. Now, given that the angle BAC is equal to the angle EDF, and that AB is to BC just as DE is to EF, what we're going to prove is that the angle ABC is equal to the angle DEF, that the angle ACB is equal to the angle DFE, that BA is to AC just as ED is to DF, and finally that BC is to CA just as EF is to FD. Now, in this proposition, Euclid delineates between two different cases, the first of which is where the angles at C and F are less than a right angle, so I've drawn them accordingly. Now if we want to prove that the angle ABC is equal to the angle EDF, we're going to do this indirectly. We're going to do this by reductio. Let's say that the angle ABC is in fact not equal to the angle DEF. Then one of them has to be greater, and we're just going to say that the angle ABC is greater than the angle DEF. Although you can just as easily prove this if the angle DEF is the greater one. But angle ABC being greater than angle EDF, then on the straight line AB, and at the point B on it, we can make the angle ABG, like that, which is equal to the angle DEF. We're going to do that by proposition 123, of course. Now, the angle BAC being equal to the angle EDF, we were given that, and that the angle ABG is equal to the angle DEF, it then must follow that the third angle AGB be equal to the third angle DFE. You can prove this just by proposition 132 and some other stuff. But again, I've talked about this before, that if two triangles have two angles equal to two angles, then the third angle will be equal to the third angle. That's very easy to prove. Okay, which means then that the two triangles ABG and DEF are equiangular, right? So the three angles are equal to the three angles. And being equiangular, by proposition 6.4, we can say that the sides about the equal angles are proportional. Namely, that AB is to BG, just as DE is to EF. But we were given that AB is to BC, just as DE is to EF, which means we have two ratios which are the same with the same ratio, which means they are the same with one another, which means that AB is to BC, just as AB is to BG. Now, if the same have the same ratio to two different magnitudes, then the two magnitudes will be equal. That is proposition 5.9. So we can say that BC is equal to BG, that. And if BC is equal to BG, then the triangle BCG is an isosceles triangle, which means that by proposition 1.5, the angles at the base are equal to each other, so that we can say that the angle BCG is equal to the angle BGC, like that. But we assume that the angle BCG is less than a right angle, right? That this is the first case where the angle at C is less than a right angle, which means that the angle BGC, which is equal to it, must also be less than a right angle. Now, the angle BGC being less than a right angle, and the sum of angle BGC and AGB being two right angles, that's proposition 113, because the angle BGC is less than a right angle, then the other angle, AGB, must be greater than a right angle. But we had shown that the angle AGB is equal to the angle DFE, which means that the angle DFE must also be greater than a right angle. But we have it now that the angle DFE and the angle DFE is simultaneously less than a right angle. This is the first case where that was assumed. But it's just been shown to also be greater than a right angle, so it simultaneously must be less than and greater than a right angle. This is manifestly absurd, which means then that the angle ABC is equal to the angle DEF. Now, between the two triangles ABC and DEF, we have two angles equal to two angles, namely the given fact that the angle BAC is equal to the angle EDF, and what has just been shown that the angle ABC is equal to the angle DEF. It then must follow that the third angle ACB is equal to the third angle DFE. Again, that's by proposition 132 and some other stuff. So the two triangles ABC and DEF are equiangular, which means, again, by proposition 6.4, that the sides about the equal angles must be proportional. So we can say that BA is to AC just as ED is to DF, and that BC is to CA just as EF is to FD. And this is all that we wanted to prove. We wanted to prove that the two triangles ABC and DEF are equiangular and have the sides about the equal angles proportional. And we've just shown that, which means we are done with the first case. But there is a second case. The second case being that the angles at C and F are in fact greater than a right angle. So they would be obtuse angles. And this shall look something like that. So we have A, B, C. So the angle at C is an obtuse angle. It is greater than a right angle. And similarly, we're going to have the triangle DEF, also an obtuse triangle, DEF. And we're given is going to remain the same, namely that the angle BAC is equal to the angle EDF, and that AB is to BC just as DE is to EF. Now, the angle ABC, if it's not equal to the angle DEF, it must of course be unequal to it. And if we have two things that are unequal, one of them of course is going to be greater. So again, we're just going to assume that the angle ABC is greater than the angle DEF. But again, you can just as easily prove this if the angle DEF is the greater. But we're going to say that the angle ABC is greater than the angle DEF, which means again, we're going to make on the straight line AB and at the point B on it, the angle AGB equal to DEF, like that. So the angle ABG is equal to the angle DEF like that. And similarly, we can prove that BC is equal to BG. This would just be going through the third and fifth steps again, showing that the two triangles ABG and DEF are equiangular, which means that their sides are proportional. Like AB is to BG just as DE is to EF. But again, we were given that AB is to BC just as DE is to EF, which means that AB is to BG just as AB is to BC, which means by 5, 9, BG and BC are equal. And again, by 1, 5, because now the triangle BCG has just been shown to be an isosceles triangle, the angle BCG is equal to the angle BGC, that. But the angle BCG in this case is greater than a right angle, which means that the angle BGC, which is equal to it, is also greater than a right angle, which means by a property of magnitudes, the sum of these two angles is going to be greater than two right angles, so that the angle BCG plus the angle BGC is going to be greater than two right angles. But we know from proposition 117 that if you add two angles of any triangle together, they must be less than two right angles. We have it the case that the angle BCG plus the angle BGC is simultaneously greater than two right angles, as has just been shown, but is also less than two right angles, as is shown by proposition 117. So we have the angle BCG plus the angle BGC being simultaneously greater than and less than two right angles. Again, this is manifestly absurd. And so we can say that the angle ABC is equal to the angle DEF, which means by a similar method, we can show that the two triangles ABC and DEF are equiangular. And again, by 6-4, if two triangles are equiangular, then the sides about them are going to be proportional, which means that in the end, we can show that the angle ABC is equal to the angle DEF, that the angle ACB is equal to the angle DFE, and that BA is to AC just as ED is to DF, and that BC is to CA just as EF is to FD. And again, this is what we wanted to prove, which means we are therefore done with the proposition, therefore, etc., QED. Now this is going to be the final similarity theorem within the elements, and this is going to be, well, what do we have? We have one angle equal to one angle, and two sides which are proportional to two sides. So we can say that this is the side-side angle similarity theorem, or the angle side similarity theorem, which is not a thing I can say. So we're going to call it the side-side angle similarity theorem. Now, I've got nothing more to say about this proposition, so I'll end the video here and move on to 6.8.